Welcome to this presentation on count distinct elements in every window. Today we will walk through the problem statement, approach, algorithm, C++ code implementation and time complexity for solving this problem efficiently. Let's begin by understanding the problem. Given an integer array ARR and a number k, we are asked to find the count of distinct elements in every window of size k in the array. For example, if the input is an array like 1, 2, 1, 3, 4, 2, 3 with k equals to 4, we need to determine the number of distinct elements in each of the sliding windows of size 4. Here's an example to clarify. Given the input array containing the elements 1, 2, 1, 3, 4, 2, 3 and window size k equals to 4, the output will be an array representing the count of distinct elements in each window. The result is 3, 4, 4, 3. In the first window, we have 1, 2, 1, 3, which gives us 3 distinct elements. In the second window, we have 2, 1, 3, 4, giving 4 distinct elements. Here's another example with the input 4, 1, 1 and k equals to 2. In the first window, we have 4, 1 which has 2 distinct elements. In the second window, we have 1, 1 which has only 1 distinct element. In this case, the array is 1, 1, 1, 1, 1 and the window size is 3. For all windows in this array, there is only one distinct element. So the output is 1, 1, 1. Now let's discuss the approach to solve the problem. We will use a sliding window technique where we slide a window of size k across the array. For each window, we will count the distinct elements. To achieve this efficiently, we use a hash map which will store the frequency of each element in the current window. In the sliding window approach, when we move the window from left to right, we remove the leftmost element and add the new element that enters the window. The key idea is that the hash map will help us keep track of the frequencies of elements efficiently. Let's now see how we can implement this approach in an optimal way. We need to update our hash map efficiently by removing the frequency of the element that is sliding out of the window and increasing the frequency of the new element that is entering the window. Here's the algorithm in a nutshell. First, we initialize the first window of size k and populate the hash map with the frequencies of the elements in this window. Then we slide the window one step at a time, updating the hash map accordingly. After processing each window, we store the size of the hash map, which represents the count of distinct elements in that window. Let's now look at the C++ code implementation. The first step is including the necessary libraries IOStream, unordered map, and vector. We will use an unordered map to store the frequency of elements and a vector to store the final result. In this part of the code, we initialize the hash map for the first window and add the frequencies of the elements in that window. Once we have populated the hash map for the first window, we push the size of the hash map to the result vector. Now for the sliding window part, we'll loop through the array starting from index k For each new element entering the window, we update the hash map. If an element leaves the window, we decrease its frequency. If the frequency becomes 0, we remove it from the hash map. Then we add the count of distinct elements to the result. Let's break down the code further. The unordered map stores the frequency of each element in the current window. For each slide of the window, we efficiently update the hash map by adding the new element and removing the old one. The size of the hash map gives us the number of distinct elements in the current window. In terms of time complexity, this approach runs in big O of n, where n is the size of the array. Each element is processed at most twice, once when entering the window and once when leaving it. The space complexity is big O of k because we are using a hash map to store up to k distinct elements in the current window. Let's now walk through the example. We have the array containing the elements 1, 2, 1, 3, 4, 2 and 3 with k equals to 4. In the first window 1, 2, 1, 3 we have 3 distinct elements 1, 2 and 3. In the second window 2, 1, 3, 4 we have 4 distinct elements 1, 2, 3 and 4. This continues for the remaining windows and we get the output 3, 4, 4, 3. In conclusion, we have solved the problem efficiently using the sliding window technique and a hash map. This solution has a time complexity of big O of n and is ideal for solving problems that require window-based operations on arrays. We can apply this approach to other problems like finding subarrays or substrings with distinct elements, making it a powerful tool. That wraps up the presentation. Do you have any questions? Let's discuss some of the challenges or optimizations that could be considered for this problem.